Hi, once again, this is JD Williams, and last time we had a brief introduction to what applied optimization is, why we need to do it, and we explained some um, terms that will be required for us to know before we start solving some problems. So here today, we would like to solve a problem here, and we can see the problem here. Problem 1.22. We'll try to solve this problem. Now, the way we're going to solve this problem is this. We will first do the build the objective function and constraints, know how to do that. Then I'll do two questions. This is the first one. This is the second one. I'll try to solve these two questions. And then in the next screencast, we will develop a MATLAB code for plotting them and having a graphical solution. So that's the way we're going to solve this question. So let's go in immediately. Now, the challenge with most of this optimization problem is to develop or to craft a mathematical model that best captures everything that is being said in the question. Let me say that again. Where the challenge is, most of the time, is not in the graph. It's also not in the MATLAB code. These things are pretty easy. Sometimes the codes are given. In fact, there are MATLAB functions for optimizing. So it's not really that. It's in understanding the question and crafting it to become a mathematical model. That's where the problem is. And hopefully we'll be able to overcome this problem together. So if you look at this question, let me say something again. An important rule that works for me is this. Make sure you use all the numbers given in the question. Anything that is given in the question is important. All information given in the problem. Sorry, let me, in the problem are important. This is key. Let me change these to problem. So it's not really a question, it's a design problem. Okay, all the problem that are given in the question are important. I mean, all the numbers given in the problem are important. This is important to know going forward. Okay, so let's read this question and try to understand. In July, Venkat's Fruits Orchards usually sees a scheduling problem. Both cherries and blueberries ripen around the same time. A cartload of cherries sells for 2,750. The cartload of blueberries fetches 1,750. The farm must deliver at least a half cartload of cherry. Now, numbers are coming in here, right? The first thing we want to notice is what is being said here expressly. It says a cartload, it's just red, a cartload of cherries sell for 2,750, while the cartload of blueberries fetches 1,750. The farm must deliver at least half cartload of cherries and one cartload of blueberries to the local supermarket. 3 persons can pick 2 cartloads of cherries, and in a day, while one person will pick a cartload of blueberries in the same day. That's interesting. So only 46 people show up for work during a day, during that day. So you notice that everything is per day. See, right? That's the basis of our units, per day. Okay, per day. Right. One cartload of cherry is contained in 4 pallets, while the same amount of blueberries occupies 6 pallets. There are 251 pallets. Each picker is paid $45 per day. Okay. The packaging and the storage can handle at most 30 cartloads per day. So our task here is to set up an LP. An LP is linear programming for the orchard to maximize profit. So straight away, our task here is to maximize some profit. So we first of all need to find an expression for that profit, and then we'll need to go on ahead. So the first thing we will do here is, so let's write here solution. The first thing we're going to do is to set up before we can set up the linear programming solution for this problem, we need to have a sound understanding of what is required. Okay, so it says a cartload of cherry sells for $2,750. So let's say let cartload of cherries equal x1, right? So that is a design variable. Let it be x1. That's what we want to find out, right? I want to find out the number of cartload of cherry and the number of cartload of blueberries that will maximize the profit. In other words, how much cartload or how many cartload would I need to deliver in a day to maximize my profit? That's what the question is asking. So let cartload of blueberries equals x2, right? Okay, and let's move on. And we need to understand that the revenue, right? It says one, look at it. It says a cartload of cherry sells for 2,750, which means if one sells for 2,750, then two of a cartload of cherries sells for that. So, and I've represented that with x1. So 2,750 x1 plus 1,750 for blueberry x2 is my revenue here, and this is what I'm trying to maximize. Revenue, right? This is what I'm trying to maximize, right? But that's not the end. The game is the question is not over. He says so let's go to the next line. So we've been able to write an objective function for that. Why the cartload of blueberry fetches that? Now, the firm must deliver at least a half of cartload of cherries, and 1 cartload of blueberries to the local supermarket. Half cartload of cherries and 1 cartload of blueberry to the local supermarket. So straight away, I can go ahead and say, right, where's my mouse? I can go ahead and say that half, to the local supermarket. So x1 is, it says, look at it again. Where's that question? Sorry. the firm must deliver at least half, right? At least means it can go beyond that. Please don't lose me here. It can go beyond that. So you can say x1 is greater than or equal to 0.5. That's very important to know. And x2 at least 1 is greater than. If it says at most, it means it can't go beyond that, right? It can't go beyond that value. So here we would say at least 0.5 x1 and at least. So we've gotten some kind of constraint here, right? Let's call that G1. Okay. Now, let's go back to the question again. The firm must deliver at least half cartload of cherries and 1 cartload of blueberry to the local supermarket. 3 persons can pick 2 cartloads of cherries. 3 persons can pick 2 cartloads of cherries. Please note this. In a day, while 1 person will pick a cartload of blueberry in the same time. Okay, so then if 3 persons can pick 2 cartloads, can pick 2 x1s, right? 2 cartload of cherry in a day. Hypothetically, how many people can pick 1 cartload? So we're saying, look at it, look at the math. Look at the math. If 3 person can pick 2 cartload, 2 x1s, or let's say 2 cartloads of cherries, right? How many persons can pick 1? I just do a simple cross multiplication there. So you have 3 over 2 equals x persons, and that is 1.5 persons. You know, this is not really practical, but it's essential for calculations right now. Okay, so don't get lost here. Is 1.5 persons will pick and why do we want 1? Because you see, it says, the question, let's go back here. The question says the firm must deliver at least half blah blah. Then 3 person can pick 2 cartloads. I mean, so you have to break this down here, break that down, so that you can find 1 cartload, because its counterpart, which is blueberries, it's 1 person. So we're dealing with 1 person per day here, or we're dealing with how do I explain this? We're dealing with so we say 3 person can pick 2 cartloads of cherries, but I'm really interested in 1 cartload of cherry. I'm not interested in the 2. It's lumped up here. I need to break it down. So I want to find how many persons can pick 1, and to do that, I need to do this simple math here to be able to break it down. So when that is done, then we know that it's 1.5 person that will be responsible, or 1.5 person that will be responsible for 1 cartload of cherries. Does that make sense? Okay. All right. So let's go back to the question. Go back to the question. Look at it. Only 46 people show up for work during the day. Only 46 people show up for work in a day. So that means essentially that if there are only 46 people that show up for work in a day, then if 1.5 persons here, if 1.5 person picks x1 in a day plus one person picking X2 cartload of blueberries in a day, then they must not go beyond 46 persons. That gives me another constraint right there, right? They must not go beyond 46 persons. Is that clear? Does it make sense? So first of all, we first found out that okay, 1.5 persons are needed for one cartload per day, right? So if I need to know the number of people that picked one cartload of cherry per day, then I need to know the number of cartloads that are picked. Then I'll know the number of person that picked it. So when you multiply that together, that's what we're saying here. So all these are per day, per day, per day. Okay, let's go on a little bit more per day. So now one cartload of cherry is contained in 4 pallets, while the same amount of blueberries occupies 6 pallets. So if we need to know and it says there are only 251 pallets. So if we need to know the number of pallets that are used per day, all we need to do is to use those constraints given to us and say, okay, well, there are 4, it will be 4x1, 4 pallets for cherries. And since we want to know the number, now our design variable is the number. Don't forget that all of these x1 and x2 are numbers of cartload. So 4 pallets that times multiply by x1 number of cartloads of cherries per day will tell us the number of pallets that is used per day. Does that make sense? Plus 6x2, that's also given, right? Must not be greater than 251 or equal to 251. Okay, this gives me another constraint right here. All right, okay, and now let's go on. Let's go on. Where is my let's go back to the question here. The last thing we need to do, you say each worker or picker is paid $45 per day. Whoa, $45 per day. Now we need to understand what is being said here. He says each picker is paid $45 per day. That is some kind of cost, because now I'm paying and giving money out, right? That's a cost. Okay, it means that something needs to be done to my profit. So after the day's profit, I must pay the workers, and each one of them must take $45 per day. So then we need to estimate the cost. So the cost here will be, remember that I have 1.5 workers picking a cartload of cherries, plus then I have just one worker picking a cartload of blueberries. In a day, these guys must be paid $45, so that the cost will be 45 into 1.5 x1 plus x2. Right, this is my cost. Now what does this portend? Right, that my profit is not complete until I take away the cost. So I'm going to say revenue minus cost. So once I do that, then my revenue is, well, everything stated above, 2750x1 plus 1750x2 minus the cost. So I'm going to use that right there. My cost is 45, 1.5 x1 plus x2 right there. This now is my objective function. This is what I'm trying to This is my real profit, and this is what I'm trying to maximize right there. So to put everything together, make it a little bit more clear for clarity, I'm going to now say that I'm going to say maximize profit. I'm going to say f x1, x2. It's a function of those two independent variable, and 2750x1 plus 1750x2 minus 45. 1.5 x1 is x2. This is my objective function that I'm trying to. This is what I'm trying to maximize, the profit. And to get the profit, I need to take away the cost. If you stop at here without considering this, right, your optimization problem will not be complete and it will not be adequate. So it goes back to what I said earlier. If you remember this, make sure to use all the numbers given in the problem, because it's so easy to skip this last one. And it's so easy to also skip this one right here that says the farm must deliver at least a half cartload of cherries and 1 cartload of blueberries right here. It's so easy to skip these guys, right? So putting everything together, we've written that. So we now have our objective function right here, and subject to the following constraints. Subject to labor constraint. Well, the labor constraint says, well, remember it's inequality constraint, a function, x2. Then that is 1.5 x1 plus x2, and that must be less than or equal to 46. Then we have storage constraints, which has to do with the, oh, I missed something out. So let's go storage constraint. Remember that here it says, did I have that here? Did I miss anything out? Where's the, okay. Yeah, sorry, I missed this out. The packaging and storage can handle at most 30 cartload per day. So, well, then, yeah, I know that that is there somewhere. So storage constraint says that both, sorry, let's call that G2. Let's call that G2, X1, X2, that both cartload of cherries and the cartload of blueberries must not exceed 30 per day. Yeah, it's right there. Look at it. Right, look at it. It says, sorry, that's another question. It says here, the packaging and the storage can handle at most 30 cartload per day. It means combine all the cartloads per day, it should not be more than 30. Both for cherries and blueberries. Right, so that's why we have that there. What other constraint do we have? The pallet constraint. Pallet constraint. Well, we can call that G3 and say X1, X2. And the pallet constraint is the one we have here. Let's say 4x1 plus 6x2 should be less than. So 4x1 plus 6x2 should be less than or equal to 251, like so. And then we put our x1 is greater than or equal to 0.5, and x2 is greater than or equal to 1. What are those? What are those actually? These are the ones it says a cartload of cherries sells for that. Well, a cartload of blueberries sells for that. The farm must deliver at least a half of cherry and one. So that's delivery constraint. So we have it there. Delivery constraint, which may serve as a side constraint too. So I can say delivery constraint. Now, the whole thing gives us our helpy formulation, and then we're good to go. We want to find the value of x1 and x2 that maximizes this thing here. I hope you enjoy this screencast. When next we meet, I will solve this question, the second question right here. And once we solve that, then we will go ahead to MATLAB and see how we can use graphical solution to solve this problem. Straight away, you can go ahead and solve it analytically right here. But it's easier when and you see a lot, it becomes clearer when we go to MATLAB to see how it works. Thank you very much. If you feel like subscribing, please go ahead and subscribe. If not, that's also fine. Thank you.